recording, and let's get started. So hi and welcome everybody who has joined us for our Ask Tom session today, which is part of the Oracle Spatial Technologies series. My name is Karin Patenge. I'm here with Denise Marek. We are both product managers in the Oracle Spatial and Graph team. The session today is dedicated to those intending to use or already use Python to work with data, or more specifically with spatial data in the Oracle database. During the session, we encourage you to put your questions in the Q&A. There are more colleagues who have joined us besides Denise and I who can take care of your questions during the session. And just to make you aware of it, Denise will also share the links we have on the slides and we are using in the demo part, and we'll put it in the chat so you can grab it from there and store it. Okay, so what are the questions we want to cover today? By the end of this session, you hopefully have a good understanding about how you can use Python to access spatial data in the Oracle database, to visualize spatial data, to query spatial data, and to use spatial data in advanced analytical workflows. Before we start talking about Python, let's recap some basics. We have seen in the previous session that in the previous sessions actually, that the Oracle database contains many features to efficiently manage and use spatial data along with any other kind of data. There are specific data types and models available to store and access spatial data like places or any kind of geometry, like satellite images, point clouds, networks, and other spatial data. Many applications include interactive maps that visualize spatial data. The Oracle data type that manages geometry is called geometry. You can find it here on the left side. There are many spatial functions and operators to work with geometries. Those are, for example, used for in proximity searches, such as the nearest neighbor or within distance search. Other operators or functions are used to discover topological relationships between geometries. You can access spatial operators and functions directly using SQL, using PySAL, or as in our demos later on, embed SQL in your Python code. The well-known text representation of geometries, which you can see on the lower right part, is a standardized textual representation of geometries and can therefore be treated as CLOP. You will also see later on in our Python notebooks how we make use of this representation of spatial data. I would also like to remind you that we have talked about reference architectures available in the Oracle Reference Architecture Center, and we have integrated a reference architecture to build a kind of simple geospatial data platform. And you can see the logical view of that reference architecture in the picture here. And going forward, you see here which services are used to build the geospatial data platform. And at the center of this geospatial data platform is an autonomous database. On the access and interpretation side, there is Spatial Studio deployed, and of course, as part of the autonomous database, you also have access to a low-code application development environment to Apex. This reference architecture is available by automation, so you can just go to the web page, click on Deploy to the Oracle Cloud, and then all the resources are automatically built using Terraform script in your Oracle Cloud tenant. And I also want to mention that this reference architecture uses resources that can be always free resources on the Oracle Cloud. So much for the basics, things that we had already covered in the previous sessions. Let's talk about Python and the Oracle database. So the Python driver for the Oracle database allows Python programs to connect to and use data managed in the Oracle database. The driver, by default in the new version called Python-OracleDB, is now a SYN driver, which means that it doesn't need any client libraries to be installed. You can, of course, use this driver together with the client libraries, and then you can choose to run the to use Python in a SIG mode. The previous name of this Python driver used to be cx_oracle. It's been around for more than 20 years. It was renamed last year, so it's now called Python-OracleDB, and you will see on the next slide how to make use of that Python driver. And here you can see it. There is a simple installation using pip to install that driver, and here you see that even though the new name is Python-OracleDB, the actual package is called OracleDB, and the way you install it is how you can see it here. Then, of course, you want to use the Python driver, and for that you need to import it via the import statement. And then connecting to an Oracle database, you simply provide the connect, or you simply use the connect method, providing the credentials for the specific database user and the service name to connect to it. There are actually two modes we recommend to do the connection. The very easy one is the walletless TLS connection, which is only using the username, the password, and the DSN. And there is the connection using a wallet, a database wallet, which is kind of known from the autonomous database, where beside the username, the password, and the DSN, you also need to configure where the TNS names can be found, and the wallet location and the wallet password. Here are some useful links where you can find many more information about Python and the Oracle database, the Python driver itself, the documentation, and Christopher Jones is the frontman of the Python driver for the Oracle DB, is also having his own Medium blog. So please check these resources for any further information. Sorry, wrong key. Okay, let's talk about a few Python libraries to work with spatial data in particular. There is a whole ecosystem of geospatial libraries already built for Python. We are going to use in our demos today just a few of them to give you kind of feeling how you can work with spatial data, what these Python libraries are doing in terms of manipulating, visualizing spatial data, or converting spatial data, or also using it for advanced analytic purposes. And we have chosen a few of the libraries. The one is Shapely for manipulation and analysis of geometry data, or planar geometric objects, or vector data, we also call them. It can make use of different spatial data formats like JSON or GeoJSON, well-known text or well-known binary. We are going to show you how to handle GeoJSON and well-known text. We are also going to use GeoPandas, which is an extension to Pandas that allows spatial operations on those spatial data by building a geodata frame. Then we are going to use matplotlib for some visualizations, and for some more advanced visualization, we are going to use Folium. And Denise is going to use PySAL and map-classify to talk about advanced analytics using Python with spatial data stored in the Oracle database. There are many more libraries in that area. The list is probably not complete. We've tried to put a few of them together, or the most important, let's say. Denise is going to share some links on it, so you can check those out on your own for the purpose you need. Okay, so before I go over to with the first demo, let's just see whether there are any questions. And so I don't see any questions. Is anybody here having a question regarding the basics in terms of the Oracle database, the basics in terms of Python? Just let us know. Okay, if not, then let me just stop the presentation here and start my notebook and talk about handling spatial data that are stored in the Oracle database. And here I have an autonomous database instance, which we are going to use together with Python. One thing that is additional to the geospatial data management platform I was talking about earlier, is that we are using this data science cloud service available on OCI. And there we have created a project called Spatial Workshop. This has a notebook session, and then we can open this notebook session, and when doing so, this is where we are getting. And I'm going to take over the first demo, and Denise is later talking about more advanced features using the other libraries I mentioned before on the slide, such as PySAL and map-classify. So let's get started with it. So we want to connect to an autonomous database because this is where spatial data are stored. I have two different schemas containing spatial data, and we're going to use some of the libraries I've mentioned before, like Shapely, Folium, and matplotlib in particular. In order to use those libraries, we of course need to import them. I will do this along the way. Once I need them, I'm going to import those. But of course, importing the libraries here, my notebook requires to have them installed before. in my Python environment. So let's get started with importing the Python driver for the Oracle database. And here I have a simple method to read the connection details from a configuration file, and then providing the connection details to that SYN driver, and then opening a cursor in the Oracle database. And to make sure that I'm connected and everything's fine, I'm just running a simple statement to see whether I'm getting back the result I'm expecting. When we work with spatial data in the Oracle database, specifically with geometries, we need to register the SDO geometry columns in the so-called user SDO metadata. SDO is short for spatial data objects, and there is a view which can be updated that belongs to each user, where we can register the metadata. And here is just the signature for the insert statement. You provide the table name, the column name, and the dimension for the longitude and latitude value, or the coordinate reference, the extension for the coordinate reference system. We are going to use here in our sessions two reference systems. One is this so-called WGS 48, which is represented by its number 4326. And let's see which tables we have registered as containing spatial data. And here you see the list of tables with their SDO geometry column. And this is easy to understand. We have address data, we have counties, we have we have other data. And here you see something that probably doesn't look familiar to you. This is an artifact coming from the use of Spatial Studio, and Spatial Studio actually provides, as part of the metadata, a function that converts longitude and latitude values stored in a table into a geometry object. And this is what we are doing here, using that function and store it in the metadata to make sure that we can use it properly in our spatial queries later on. And here, just to be complete, is the function used to create a SDO geometry object out of longitude and latitude value for this coordinate reference system. So let's go further and import some well-known text data. Well-known text, as said, is a very common and standardized representation of spatial data, and we're using Shapely to import well-known text into our notebook and run some further processing on it. And here we just simply define a geometry by using the well-known text representation. This is a representation for a polygon, and if we just visualize this geometry, you can actually see that we have 5 vertices forming that polygon. And for a polygon, you always have this restriction that the first and the last, the coordinates for the first and the last vertex need to be the same. So you need to have a closed polygon. And it's geometry, as you can see here. So this is one possibility to work with spatial data by taking the well-known text representation. But let's see how we can access SDO geometry data that are stored in the Oracle database. And for that purpose, I have a helper function here that takes an object relational representation of data that we are using to express geometries in the Oracle database. And this dump object function turns this object relational representation into a textual representation, and this is what we are going to display here. So we this object is made of several parameters: the geometry type, the spatial reference ID. Then, if we have a point, then we have the vertices for that point, the coordinates of the point, and for lines or polygons, we have these two parameters, SDO element info and SDO ordinate, who express how the vertices are actually forming either a line or a polygon. Now we want to convert this SDO geometry into well-known text, because this is a very easy way to work with spatial data, having the well-known text or the GeoJSON representation, and this is what I'm going to do next. So here I have a simple select statement that does two things that are related to the spatial features and functions. The first thing is that I'm using the SDO_geom.SDO_area to calculate the area of a polygon. And here the data set is zip code areas, and the filter is set on the state of Bavaria. So I have only the zip codes for Bavaria. And the second function that is related to spatial data is that I'm taking the SDO geometry object, which is this one in the table, and convert it into well-known text and give it a name, an alias here called geometry. And I only want to have the largest zip code area, and this is what I'm going to first print out, the actual data returned, and of course I can also plot the shape of that zip code area using the well-known text support provided by Shapely. Now we are going to use GeoPandas to build a geodata frame out of our result sets that are returned by running a SQL query. So again, we are using the zip code data. We are also setting the filter to Bavaria. And now we are taking the geometry value and turn that into a GeoPandas frame. And for that, we have this statement here that applies a lambda function to turn to extract the well-known text representation of this geometry, and to later on to provide it for visualization as well. So we are going to run that, have the result set here, and the polygon, the well-known text representation for the polygons. We can see that it is a GeoPandas data frame, and now we are going to use matplotlib to visualize the result set. And what we can see here now is that we have all the zip code areas for Bavaria on our diagram. So this is a very simple way to visualize spatial data. So we have seen how we can make use of well-known text directly. We have seen how to retrieve SDO geometry data from the Orica database, how to convert those into well-known text, and how to plot them on a very simple map. And now we want to use the same data set to do some spatial analysis. And here we are going to find out topological relationship, specifically which postal code areas interact with the largest postal code area in Bavaria. And we had extracted this largest postal code area in Bavaria before. It has the postal code 82467, and we are going to use the SDO any interact function to compare postal code areas against these specific postal code areas to find the neighbors for it. Let's do this, and then we're going to use the same approach as before to first show the result set, and then also to visualize the data using matplotlib. And here you can see the result of it. This is the largest postal code area here with the number 82467. And these are all the neighbors around this postal code area. And just in case you're wondering if there is a neighbor missing here on this border, it isn't, since the postal code areas are restricted to Germany, or the data set is restricted to Germany, and this part here already belongs to Austria. Okay, so much for working directly with geometry data in the Oracle database. Now I want to show you also how to work with longitude and latitude values directly, rather than making geometry or turning this into an geometry object. And for that, I'm doing two things. First, I'm importing Folium for later representation of the longitude and latitude values, which represent points. And I'm using a different data set, and this is a data set representing weather stations in Germany. And part of this data set is the longitude and latitude values expressed as numeric values. And we can take them directly and turn those into a data frame, print the data frame out, and then using Folium to plot the result set on the map. Let's do this. And now we can see here, this looks a little bit different, more of a map than what we've seen before with matplotlib. And if you go further, zoom further in, you can also see where the weather station is, because it's labeled with a name. And this is how you can directly plot location information on this way, point information on a map. And with that, I want to close my demo part and hand over to Denise for the more analytical part.
Thanks, Karen. Let me just get my screen set up here. Excuse me. Great. Karen, can you just confirm that you can see my screen? Or anybody else?
Yeah, we can see it.
Okay, thanks, David.
Sorry, I was confused. Yep. Okay.
Thanks. Oh, I see that we have a question. Okay, thanks, Miriam. Okay, so as Karen mentioned, so what I'm going to do is show us how to load data from the Oracle database and import data from an external data set. And then we'll use this data to explore the regions of the US with the most car accidents that occur at low and high speeds. So let's just jump right in. So So the first thing that we're going to do is import a number of libraries that we're going to use during this demo. And as Karen showed us before, we're going to connect to the Oracle Autonomous Database. We already imported the Oracle DB up here above. And we'll get our username and password from a file that we have set up elsewhere. And then we'll use that data to connect to the database using our user spatial user and a password and a DSN that are stored separately. So then we'll start loading data that is stored within the database already. And the first data table that we're going to load is called US Grid. And this is going to provide us some geographic tiles covering the continental United States. So we'll connect our cursor and select all of the data from the table US Grid. And that will return some data letting us know that we've gotten that data set. Okay, and then we'll execute this SQL function that gives us some information on the geometry so we can ensure that we're getting this data set properly, and we'll fetch all that data. And then we're going to simply plot this grid of the continental United States from the table. So we get a nice little grid here where we can see the continental United States. Great, so we have that table all set and ready to go. And then we're going to pull in traffic accidents data for the US. So again, we'll get all the data set information. So we can see what kind of data types we have here and what the table names are, or excuse me, the column names are. And then we can see what some of that data looks like here. So we can tell here that we can see if speeding was involved as a factor of the accident, if there was distracted driving, if the person involved in the accident was male or female or both, if they had a valid license, and some other information that would be interesting to drill down into. Here we're going to import some unemployment data for the United States for a demo that we might not have time to get to today. So again, we'll import this data. We can see the column names and the data types here. And we can see what that data looks like in a table form. And once again, we'll import this data and we can see the same sort of information that we showed above. Okay. And so what we're going to do here is import or ingest other data sets used for this demo. So this data set that we're looking at right now comes from lib.PySAL, the examples data set. So we're going to import that data. So this data doesn't already exist within the Oracle database. We're getting it from a separate stream. And we can see all of the different data sets that are available from this function and import all of the available data sets. So we have information about Airbnb rentals in the city of Chicago, information about Boston housing, US income information, Virginia counties, we have a shapefile for that, etc. So we're going to look at the US income data set, and we can see here a little description of what's in there, including a polygon shapefile of the continental United States, which we're going to use in our demo. So we're going to use that data set here, and we're going to plot the United States. So we're using the grid setup that we showed earlier in the demo, and now we have an overlay of the states. So you can see the outline of all the states in the continental United States in the little grid that we have here. That's good. Oh, it looks like we have a question. Oh, no question. All right, so let's do some queries and do some spatial analysis now that we have all of our data set up. So the first query we're going to do is to list the percentage of traffic accidents that are involved speeding and per the tile. So let's look at this data set. So we'll be putting the data together using the with statement from different tables. So we're using the table forest PySAL, and we're using the data table US grid. So we're going to use those two data tables to find out some information that we're interested in. In this case, whether or not speeding is involved in this accident. And that gives us a data table.
Denise? Yeah, can I
oh, I missed the part.
mention something? Yeah.
Sure.
So the use of the stdio-util package to convert to GeoJSON here. So,
yes, thank you. Thanks for looking out for me. So we're using the stdio-util package here to convert the stdio geometry to JSON, and then we're going to use the shapely package to generate the well-known text. So we're using this function here, and then also down here, this is interesting as well. Did I miss anything else, Karen?
no, we just wanted to make sure that you see all the different options you have to do to convert data and to prepare those to be used with Python, with the
Yes.
Python libraries.
Thanks. I appreciate you mentioning that. I would have been disappointed if we got to the end of the demo and I hadn't gotten there. Okay. And then we're going to be able to see the result. So here is a result of those data. So we can see the grids with accidents. The deeper the color red are the accidents that have speed as a factor, and the ones that are light of colored, like down here, speed wasn't considered a factor in accidents, or as many accidents in these grids. And then we have a few very small places where we don't have any data. So those are blue. Okay, great. So I think it's important to note that that's kind of where the spatial library functionality ends. So what we did with the spatial layer is we ingested the data so the Python can do the more interesting data analysis. So I'm going to quickly go over this, and we're not going to go super into detail here, but we're going to import another library here, and we're going to be able to use the Python functionality to do some interesting analysis. And we can get something called a Moran's eye, which tells us about the spatial randomness of the data set. And if we just go through and use this functionality, we can tell the hotspots and low spots of high speed and low speed data sets that we have. So using that data and some fancy spatial analysis, we can tell where in the continental United States we have the most accidents with high speed, where accidents are more likely to happen with the high speed, and conversely, where in the United States accidents are more likely to happen at low speed. And there we go. Karen, if you want to take control back, and we can continue with the slides. Does anybody have any questions before we move forward?
That's what I wanted to ask as well. So I haven't seen any open questions in the Q&A.
Great.
Oh, there is a question. We are not talking about RDF-lib here, so it's not part of that notebook here. So, and RDF I actually know from Resource Description Framework in the knowledge area. So, yeah, maybe we take this question offline.
Mm-hmm.
Okay, so let me share my screen. And take it from here. So we have seen in the live demo ways to use SQL to retrieve data from the Oracle database, to convert data, to analyze data, and then we can use Python to embed this SQL code and yeah, do further things like visualizing data, and especially having this notebook-based approach to analyze the data and immediately see the results of a certain analysis step, which is a very nice approach to work with the data and for those kind of analytical workflows. Okay, so one more note related to what we have seen before and related to the environment we are using here. So we have told you that the data are stored in an autonomous database, and some of the functions available for the spatial functions available are implemented in Java. And especially, we have seen the different ways to convert geometry data into other formats. And the last example was to use the stdio_utip package for this kind of conversion from geometry to GeoJSON or to well-known text. And these conversion functions require to have the Oracle JVM enabled in the autonomous database. There's a very easy call to do so, and I've included the link here with the documentation how you can enable Java in an autonomous database. And I think, Denise, you are going to share that link as well.
I did. Thanks, Karen. Okay,
so we are ahead of time. Let's summarize what you've seen, what you've learned. So we make use of the Oracle database and let the database process the or run the extensive processing, conversion functions, and also putting the data together for later analysis. You have seen that being embedded into your notebook, Python code. And Python with the many libraries in the realm of spatial data can perfectly extend and complement the capabilities you already have with the Oracle database to work efficiently with spatial data. And especially this notebook approach for data analysts is a very nice way to implement analytical workflows. So if Python is your programming language of choice, you can easily access and use spatial data that are stored in the Oracle database. And for that purpose, you use the Python driver that is provided by Oracle. You can use all the available popular Python libraries we have listed before to do more advanced stuff with your spatial data. And of course, you can use any spatial operator and function that is part of the spatial support in the Oracle database in your Python notebooks and in any kind of spatial data processing and analytical workflows. And if you want to have an easy start using the Oracle Autonomous Database together with notebooks, then just spin up the Oracle reference architecture for a geospatial data platform, create a data science notebook, and implement your Python code there. Some more information at the end with providing some more links where you can find more to learn about the Oracle database, about Python, about the reference architectures, but also the typical channels where we post new information. These are our blogs. We have moved from this blogs.oracle.com, Oracle Spatial, to the Oracle Database Insiders blogs, and have a specific category there that covers spatial information about spatial support in the Oracle portfolio. We also publish on medium.com. You find our blogs or our posts tagged with Oracle-Spatial. We also have a YouTube channel where we publish regularly interesting webcasts or sessions, for example, for the analytics and data user community, and other interesting recordings when somebody talks about spatial technologies. And we have a LinkedIn group which we encourage you to join to get information via this channel as well. Or if you prefer to use Twitter, here are a few colleagues with their Twitter handles who post regularly or who tweet regularly on Twitter. Okay, so that's the end of what we wanted to show today. I'm looking at the Q&A session. Yes, Friedrich, there's also GDAL OGR library available. We haven't used it here, but we can certainly make sure to use it in a later session or in a blog post or whatsoever to talk about it. The rest of the questions were answered. Okay, so if there isn't anything else you want to ask right now, then let's just have a look at our next session. So this is planned for the end of May. So there are typically plenty of holidays during end of April and in the course of May. So we have decided to do just one spatial office hour session in May, and this will be on May 30. Our technical expert will be Albert Godefroy. So we invite you to join that session. Will be an interesting one. We have planned to talk about using spatial data via REST endpoints. We want to go into more details about GeoJSON and some more tips and tricks of this huge box of tricks Albert has collected and worked on over the past 20 years. So it's worth to join this session because you will never get the chance to learn more about spatial than by listening to Albert. Okay, that's it for today. Thank you very much for joining our session. Denise, hope you, is there anything else you I missed to talk about, to mention, you want to mention?
I don't think so, Karen. I think you covered it all.
Perfect. Okay, then hopefully we are seeing you back on May 30th, and have a nice day wherever you are.